Chapter 9 is about Pearson Chi-squared tests. There are a bunch of these, but we'll go over 3 of them, or 2 or 3 of them, depending on how you count. The first one is the goodness of fit test, which I will just abbreviate with GOF. So the goodness of fit test is complicated because it leaves much to the imagination. And this is what makes it a non-parametric procedure. And I'll be clearer about that once we get to some examples. But it's also simple because it's basically a multinomial test. Which makes it basically parametric after you use your imagination. So under the hood. A multinomial test is similar to a binomial test, which is what we talked about in Chapter 1. And I'll explain that connection in just a little bit. So when do you use it? So it can be applied whenever your data can be categorized. Sometimes this happens naturally. It already comes categorized. And again, I'll explain what I mean by that in a minute. But in most cases, you have to divvy up the data into a finite number of categories. And then you need to be able to calculate, and you can calculate expectations for those categories under whatever you choose for your null hypothesis. Often making these categories involves, and working with the null hypothesis involves making a distributional assumption. So often the null hypothesis involves choosing a distribution. So you might think that that makes it parametric, but maybe let's not say but, let's say so. Goodness of fit testing is a bit of a P non-P hybrid. Again, I'll have to get to some examples. But before I do, let's talk about those categories. So you want to be able to build what's called a goodness of fit contingency table. So you've got to choose a number of categories C. So this is going to be a 1 by C table. And you're going to want to organize your data in such a way as your observations can be sorted into counts of the number that fall into each category. So we'll call the categories classes. So we'll have class 1, class 2, class C. And then we'll have the number of observations in each class of C classes. And so this is kind of the table. If I just kind of draw straight lines in order to make it look more like a table. So these are our observations. And then often you have a total column where you sum up, you keep track of the number of observations in each class. So that's called the contingency table. It's a very simple one, which just has one row. The case of C equals 2, with just two categories or classes, is basically a binomial test from chapter 1. Okay. So if you can divvy up your data so that it sorts itself into C classes, then the next thing is you have to boil down your want to know to probabilities for those classes so that we may model. I'm putting model in quotes because we're not choosing a model for the data itself. We are just choosing some classes, some categories, and then boiling the probabilities and the null hypothesis down, or boiling the null hypothesis down into probabilities for those classes, so that we can regard the vector of C observations as a draw from a multinomial distribution with n samples in p probabilities. So this vector of p probabilities is defining the multinomial distribution. And once we have a multinomial distribution, the expectations for each of the categories is just n times pj for j equals 1 up to c. And we will call this ej. Okay, I've only got a few more things to say before I get concrete about how this will work in a real example. In fact, we're going to do two real examples. So, particular values for those probabilities may come from a separate, usually P or parametric analysis. For example, after calculating a maximum likelihood for some parameters, so that the test can be reframed as pitting particular values of the parameter vector P0 versus it not being P0. So actually we've reframed things twice. First we have to divvy into categories, which is reframing any want to know as a multinomial model for the data involving some parameters that might be described through some distributional assumptions in order to create a null and alternative hypothesis. Now I'm realizing I've got a typo here. This should be H1. All right, finally, the test statistic is a comparison between what you've observed in each category and what you expect. So if this distance is large, you're probably going to reject the null hypothesis, but if it's small, then you're going to accept it. And remember, these EJs are related to the probabilities. We don't just do the differences, we make them positive and we normalize them. And actually, you can just get rid of the denominator and make them positive by squaring and do the whole analysis on this statistic, which is called x squared. You can do it without normalizing by dividing by EJ if you're willing to do simulation. But if you're going to do it in closed form, the math way, I'm doing things a little out of order. Usually we do the simulation and then I tell you the math way, but I want to wrap up the whiteboard part of the lecture so we can move exclusively to code after this. So it can be shown that the distribution of this statistic is chi-squared with c minus 1 degrees of freedom as n goes to infinity. So it's a little bit like a central limit theorem type asymptotic argument. And that's why these are called Pearson Chi-squared tests. In fact, everything boils down to one of these kind of statistics and this kind of distribution. But you don't need to be a clever mathematician to work it out because you can simulate. So let me go over to R. I'm going to do two examples. One of them is super basic, where the categories are basically given to us, or the classes and the categorization are given to us, and another one where we make them ourselves. So let's pop over to R. You can see my data already. So I've already got a 1 by C contingency table, a vector of observations, and these are rolls of a 6-sided die, counting the number of faces that or dots that come up on the face. So the 1 dot comes up 119 times, 2 dots comes up 90 times, 3 dots comes up 86 times, and so on. So this is sort of naturally in a multinomial setup with the classes already given to you. So it kind of makes it easier. So we have C classes, which is the length of the vector, and then the total number of rolls of the die is n. Whoops. Whoop, I gotta run that. In fact, you can, try to ignore that down there. I'm gonna get to that data later. I keep messing this up. Okay, good. Okay, so N and C, you can think about rolling dice as kind of like an upgrade of flipping coins from chapter 1. When you flip coins, you just have 2 categories, heads and tails. When you roll dice, if it's a 6-sided die, you have 6 categories. In general, we're going to have more than 2 categories, and we're going to have to make the classifications of those categories ourselves. But for this example, we don't. And so what we want to know is the die fair, right? So the die is fair is our null hypothesis versus the alternative that it's not. And we know that when the die is fair, the probability is 1/6. So we can do rep 1/6 6 times, and that would be the probabilities under the null hypothesis if the die is fair. And our expectations are the total number of flips times that probability, so that what is n? Why is n 6? N should be the sum of, oh, that's a big typo, okay. So if the die is fair, we should get, in a total of 600 flips, we should get 100 of each face on average. But we didn't get 100 of each face. We got a different number. We got these. And what we want to do is we want to compare what we observed to what we expected to get under the null hypothesis. So our test statistic is the sum of the observed minus the expected squared over the expected. So that's what we call x2. Okay, so that number is 11, and that number is meaningless unless we can understand the distribution of that test statistic under the null hypothesis. We know that it's asymptotically chi-squared because I gave you that result already, but I want to simulate first in order to, I don't know, that's how we've been doing stuff, right? We simulate and then we check that that the math works out. So how do we roll dice Well, one option is to use the sample command. There are categories 1 to C, or 1 to 6 in this example, and the probabilities are P. Right, so I can roll a dice. There I got 1, and the second time I rolled a 4, and the third time I rolled a 5, and the fourth time I rolled a 6, and so on. So that's how we roll a die one time. If I want to roll the die n times, I can do that, but now I'm going to get a huge, I better write replace equals true if I'm going to do more than one sample, and then I can get 600 rolls of the dice. And then if I want to make a table that counts how many of each one I have, I can just wrap that in a table command. So that's how you roll 600 die and then keep track of what we got, and then we could think about how that might compare, that virtual sample compares to what we actually observed. Okay, so another thing that you can do, remember we did this in chapter 1, we used individual coin flips, but then we replaced that with a sample from a binomial distribution. So you can also do R multinom and give it your parameters. You want to do one big draw of n rolls with probability P. R multinom. Okay, so that will give you similar looking rolls. That's not exactly the same numbers as we got before when we used table and sample because it's random. Look how it organizes itself as a column vector. We're going to want to use it as a row vector, so you can always drop the dimensions and turn things into row vectors if you want. Okay, so I'll do the example both ways. So you could do it equivalent two equivalent ways. I'll do my simulation the first way this time, and then we'll do it the second way next time. It really doesn't matter. So I'm going to call these my observations, capital O, simulated, table, I'll just go grab this, right? I don't need to type it. Okay. And then I need to calculate the test statistic with those simulated observations. Okay, so there we go. Oh, I better make XS, X2 S rep NaN. So there we, E. All sorts of typos today. I apologize. Okay, so this is going to take a little longer than some of our other simulations because we're doing a pretty big sample. Well, it's done already. I was just trying to fill some time by talking. But we're sampling 600 things in each iteration, so it's a little slower. Our usual visual. Okay, and you can't see that, I don't think, but I think you can now. So there's our empirical sampling distribution under the null hypothesis, and we can put our observed statistic on there. And that, I thought our observed statistic was 11. Why am I all of a sudden getting, oh, I see what I've done. Haha. I'm just having a terrible morning. I did a bad job of cutting and pasting. So let's recalculate the test statistic, and then we can remake the, oh, there we go. Whew. All right, that's a close call, right? That's in the tail of the distribution. I don't know if when I calculate the p-value, I'm going to have something bigger than 0.5 or not. So mean of x2s bigger than x2. It is right on the borderline. Technically reject at the 5% level. So we would conclude that this die is not fair. If you want to do it the math way, you can use a p chi-squared calculation with c minus 1 degrees of freedom, CHISQ, and you can see I get a very similar number. An important thing to note here is that these p-values are always right-tailed. So it's not a two-tailed calculation with these chi-squared tests. All right, so second example. In this one, it's going to be totally different. So first of all, you're going to have to go download some data on the book webpage. And if you have the data file in the same directory as your code file, and if it's not, you can always go to session set working directory to some other place if you want to. So we read in that data. I am not in the right directory, so I better do that. Okay. So I read in that data. This data has math scores for students at 100 different schools, and we're going to only look at the first school, and it also has some other data besides the math scores, but the second column has the math scores. So here are those data. In fact, I really like histograms to just quickly look at data. So there's the raw math scores for students that took a test at a particular school, at the very first of the 100 schools in the data set. And the question here that we're going to answer is it reasonable to model these data as Gaussian? So we want to know, is the Gaussian a good fit? Which is why this is called a goodness of fit test. Okay, so the first question is what Gaussian, right? Gaussian has two parameters, mu and sigma squared. So in order to do the test, we're going to have to be specific and estimate those parameters. So the best Gaussian is the one that we want to answer this question with. So we're going to estimate mu hat with y bar. I'll just call it y bar instead of mu hat. That's the mean of the y values, and S2 is the variance of the y's, and that'll be my sigma squared estimate. So now we know what Gaussian we are going to try in order to tell if a Gaussian is a good fit to these data. Now we need to convert our data and our Gaussian into a classification with, or a categorization, I guess, probably better, with probabilities. Okay, so this is where it's a bit of an art. You have to make some choices how you're going to divvy things up. For this example, I'm going to divvy things into 10 categories. If you do too few or too many, there can be some hazards, and I encourage you to experiment with that. But I've got n, oh, that's n from before. N is length of y now. N is 31. So I have 31 observations. 10 seems to me like a kind of a good number of buckets to divvy my 31 observations into, because I'm going to probably end up with like maybe 3 plus or minus in each bucket. Okay, so my buckets, actually in my own code I called them bins, not buckets. I'm going to make a sequence that goes from the smallest observation to the largest observation. So my buckets are going to span the range of the data, and then I'm going to do C plus 1 of them because I want one more endpoint in my bucket than the number of buckets that I want, or bins. The smallest one is going to be minus infinity. It'll become clear why I'm doing this when I make a plot. And the largest one is going to be plus infinity. And then all the ones in the middle let me show you what I did actually. So here I made the bins this sequence. So the bins are sort of these numbers here. But then I replaced why is it telling me that? Oh, it's because it's capital INF. I didn't even notice that it was complaining before. This is not my day. Bin not found. Bins. So I've replaced the endpoints with plus or minus infinity. All right, now I'm going to do a for loop so that I can calculate probabilities under the Gaussian distribution for these bins. So P norm bins I plus 1 with parameter y bar and square root of sigma squared. And then I'm going to take that number and subtract off the next probability. So I'm calculating the probability difference, or the cumulative distribution difference between successive bins. And then the observations that fall into those bins are just a count of the y values that are between the, or lower than the bigger bin and bigger than the smaller bin. Okay, so this might all be very mysterious. For the plot, I'm going to calculate what I call the midway, or the mids, which is just bins minus 11 plus diff bins 2. This isn't really necessary. Why is this a problem? Why is that 7? C is supposed to be 10. Maybe I never ran that code. Oh, good. Okay. Really not my day today. I apologize. Okay, here's the visual. Matplot, mids, C bind O over sum of O, and then P. And then PCH equals 20, 21, call equals 1, 2. Okay, up. PCH. Warnings. Why were there warnings? PCB. Oh, but I changed it to PCH. Okay. So here's the visual on the right-hand side. The open red circles are, you can see how that kind of has a bell-shaped curve. Those probabilities are coming from the Gaussian distribution with parameters y bar and S2. So this is what the probability should be under the null hypothesis of a Gaussian distribution, limited to the 10 buckets that we've created. So I've taken a Gaussian distribution, which is this smooth curve, and broken it into 10 discrete buckets, which should have these probabilities, which I calculated in my for loop. That was this part of it. So a difference of cumulative distributions in each of the buckets. And then I also broke my observed data into those same buckets. And those are the black dots. So the first bucket had this O in it, but I'm showing you that O normalized. So I have it on the same axis as probabilities. In order to show you O next to P on the same axes, I've got to normalize so it looks like an estimate of the probability. And in fact, under a multinomial distribution, that would be the maximum likelihood estimate of the parameter P. And then we can do a comparison. So we're boiling this all down to a multinomial test under maximum likelihood estimation. In the second bucket or bin, I've got a different relationship. I have more observations than I would have expected given those probabilities, and so on. So now that we have boiled everything down to, so that's what we're doing here. We've, I'll put a little comment, boil everything down to a multinomial NP. And this is just for a visual of that comparison. Then we can calculate the test statistic. So that what we expect is just n times p, because we've already defined n and p. And the chi-squared statistic is sum O minus e squared over e. So all of the hard work is in this for loop, and the lead up to the for loop, because we are reducing our want to know, which is really about a Gaussian, into a discrete number of categories, and that's what makes it non-parametric. Even though we used a parametric analysis to get the parameters of that Gaussian distribution, the test itself involves C categories, which is totally different. And then we are doing a multinomial style test with this chi-squared statistic that's also kind of parametric. But since we brought something non-parametric into it, these categories, and the number of which is totally up to us, and their composition is totally up to us, it becomes a non-parametric test. Okay, so I ran that code. I just need to run this one. And then I can go borrow from up above. It's the same simulation, but I just have different C and N and P. So let's just run, oops, I have made another mistake. Did I not run the E part? So what is E? So that's 10 things, and P is also 10 things, and C is 10. So oh, I did promise you that I was going to run the sample a different way. So why don't I do that? R multi-nom 1 size equals N and prob equals P. And you can do the drop part here if you want to, but we're just going to use it in a sum later, so that part doesn't matter. But you got to type R multi-nom correctly. Okay. So this ran a lot faster because the size N, which was just 31, is small. So that runs really quickly. Again, you can look at the visual if you want to, but it's not essential. This time we're definitely not going to reject the null hypothesis because we're not in the right tail at all, but we can calculate the p-value. 88%, definitely not enough evidence to reject the null hypothesis. And if you want, you can do that with PCHI SQ x2 c minus 1 lower tail equals false. SQ, I do that all the time. It's basically the same number. So the hard part is not, it's definitely not calculating the test statistic. It's definitely not doing the simulation. This is one of the simplest simulations we've done, and it's definitely not doing it the math way. What's hard, if the categories aren't given to you immediately, is this part here. Deciding how you're going to convert your problem into one that involves a 1 by C contingency table, which means deciding on the number of classes in your categorization and then how they're composed, which I did by divvying up the Gaussian in the area nearby where I had data.